demonstrate one more example to make this point about entropy principle or principle of increase of entropy. Look at this. There is a box which has two compartments. There is a partition, compartment A, compartment B, and this is insulated. So these lines which I am drawing, they signify this is insulated system. So this is isolated system because there is insulation. There is no work or energy mass or energy entering or leaving the system across the system boundary. This is remaining is surrounding. So this is your isolated system. Both these compartments, both A and B, are part of this isolated system. So here is gas, some gas with pressure P1, volume V1, temperature T1. Here it is evacuated. There is nothing here. Okay. You may recollect that we have talked about this. I am considering a case of free expansion. Go back to previous videos and you can remember this. So this is, now let's say the system will have certain entropy because this is gas molecules here and it will have certain entropy. Now what happens if we remove the partition? If we remove the partition, here there is pressure here, there is zero pressure here. So the gas in a way is going to expand, right? And it is expanding in such a way that the resistance to the expansion of gas is zero. So it's a free expansion. It's a free expansion. Free expansion is an irreversible process. Recollect all that discussion when the piston, we imagined it to be split into infinite slices. We remove one after another, one slice, and the expansion was taking place quasi-statically because it was fully restricted expansion. But this is a polar opposite. This is completely free expansion because that means there is finite pressure difference and that is causing expansion, right? It is finite pressure difference. This zero pressure, there is some pressure. So in equilibrium which is causing this process of expansion is finite. It is not infinitesimal. So this process is an irreversible one. So what will happen? The gas will occupy new volume. So if I remove this, so new state, this state 1. So for state 1, let's say there is entropy S1. For this state, entire state 1, there is state 1 means when the pressure is P1, volume V1, temperature T1. Now when I remove this, if I remove this partition, the gas would expand, the gas would occupy the new volume. And obviously you will see that the values of pressure, volume, that they are going to change, right? So it's a new state. Now what will be the entropy of the new state? This entropy will be, let's say, S2, entropy of this gas. Obviously S2 is going to be greater than S1. That means entropy of the system has increased. Now I said obviously, but why obviously? You should reflect. See, just think about it. Here there are certain molecules. Now the volume has increased. The molecules now have more freedom. They can move in. So if you recollect my video where I explain you entropy and I talk about microstates. So there are more microstates possible because there is freedom of the molecules is increased. So there are more microstates are possible. So that means entropy is more now. Entropy has increased. Volume has increased. So entropy has increased. So this process has occurred and entropy of the isolated system, this is isolated system, has increased. That's what we have said. We have been saying ds is greater than or equal to 0. This is applicable only for isolated system. If the process is irreversible, entropy of the system will increase. And this is an irreversible process. Entropy has increased. So entropy of the universe also will increase because system and surrounding is unaffected by this because it's insulated. So entropy of the surrounding is 0 because of this process, but entropy of the system has increased. So as a result, entropy of the universe has increased. Okay. So this is yet another example of entropy principle or principle of increase of entropy. Thank you.